Our third speaker is Dr. Tiffany Williams from the Glenn Research Center. We saw from Lorenzo's presentation, often in aerospace and that turbine blade that was there, we keep pushing the performance of the materials using more expensive and more durable components instead of looking at the structures. And so I remember early in my career when I was at NASA, one of the first lessons in materials to me was using some really advanced refractory materials, trying to get the performance out of that, actually having to create an entire supply chain to generate it. And 30 years later, it's very nice to see that Dr. Williams is working in biomimetic solutions in those material areas, looking at a completely different way of looking at some of the structures and some of the functions. Dr. Williams has her PhD from Tuskegee and her bachelor's degree also from Tuskegee, and in the middle there, a stint at the University of Cincinnati in material science. Multiple awards and technical societies. She joined the NASA workforce in 2010 and is a material scientist in the materials chemistry and physics branch in the materials and structures division. So, without ado, Dr. Williams.
Thanks, John. So today I will talk to you, first I'll start off by giving a very brief overview about where NASA is headed as an agency in terms of the high-level priorities and how we can hopefully use biomimicry to get us to that place. So the title of my talk is Bio-Inspired Materials and Processes for Aerospace Environments. So NASA is at a very exciting point in both aeronautics and space. In space exploration, our near-term priority is to land humans on the moon and to help build the infrastructure to enable a longer-term sustained presence on the moon and working towards the human missions to Mars. For this, new materials, structures, and devices that are more tolerant to those extreme environments will be key to help us achieve mission success. We continue making new discoveries about our solar system and beyond, and also about our sun and our planet. In the area of climate, we continue making our technologies available for the public to give more information or to give us a deeper understanding about how our climate is changing, whether related to air quality or pollution, droughts, wildfires, or melting permafrost. And speaking of climate, the aviation industry currently accounts for about 2.5% of the global CO2 emissions, and that number is only expected to grow as the demand for international and domestic air transportation continues to increase. Fuel is a significant driver of the cost of air and transportation, and so we are trying to pursue a balanced approach to balance both sustainability and affordability. One of the areas that NASA, along with others in the aviation community, are working towards is a net zero or carbon neutral growth by 2050. And so some of our efforts related to electrifying propulsion technologies will help us get to that carbon neutral growth. Another area or another project that is focused on reducing the environmental impacts of aviation relates to a project where we are trying to increase the sustainability component in almost every part of the aircraft, beginning from materials and sourcing all the way to recyclability at the end of the life. And that project is beginning to look at the use of bio-based materials for recyclability and sustainability. So with the aviation and space industries both moving in completely different directions at the same time, we know that we need novel material solutions to help us get to that point. So how can we use biomimicry to help solve some of our technical challenges? And so how I laid out my presentation, I just listed a few technical challenges and some of the biological models that could be applicable. So the first technical challenge relates to improving the longevity of electrical insulation. We are currently, for both air and aeronautics and space, looking at high voltage systems. And oftentimes, electrical insulation failure can lead to fires, power loss, a loss of life, very catastrophic failure. So there's also damage to the insulator that could be created through either handling or installation or even repair. And so self-healing materials could be an ideal application for the insulator. But there are two types of self-healing mechanisms: extrinsic approaches and intrinsic healing approaches. One of the more popular example is the extrinsic healing approach. And typically you have a material that is embedded with either microcapsules or capillaries. And so those microcapsules or capillaries contain healing agents. And so basically if a damage or a crack is detected, the contents of that microcapsule will flow into the crack and eventually cure. The issue with this approach is that healing is often limited to a one-time healing cycle. Another issue relates to the fact that usually there's a loss in mechanical strength at the point where that damage took place and even the healing took place. So one ideal approach is to use an intrinsic healing approach. And by intrinsic, I mean that basically reversible bonds are a part of the chemical structure of, in this case, a polymer. So basically, if there's a damage that's detected, the bond will break and reform without experiencing a noticeable loss in performance. And when we looked at a similar a polymer with this type of chemical structure, an ionically cross-linked copolymer, we noticed that we were able to recoup, after damage, we were able to recoup the mechanical strength and also the dielectric strength of and the dielectric properties of that insulator, over 95%, which is very impressive. The issue with that particular polymer system that we looked at said it had low thermal properties for our application, but there are other polymer chemistries that also contain the reversible cross-linking, such as silicones, which are also a class of polymers used in electrical insulators. Noise is another technical challenge often experienced in the aviation industry. And so NASA Glenn researchers have been able to successfully develop a prototype of acoustic liners based upon inspiration from the natural reeds. And basically, they found that by incorporating this particular type of prototype, they were able to achieve higher acoustic absorption properties over a broader frequency range through that particular model. Aircraft icing is another technical challenge that we often experience, and icing can actually lead to not only reduced lift, but also higher weight and drag forces. And depending on where this icing is located, it can be ingested and cause a power loss and also a safety hazard. Current mitigation strategies include either antifreeze sprays or pneumatic heating. Both of those have its challenges, either related to environmental concerns related to the antifreeze sprays or the added power and weight from implementing a pneumatic heating approach. But one biological model that could help with this is protein mimetics. Protein mimetics is very popular in the biology and pharmaceutical industry, but we rarely talk about it in material science. And there are certain insects and fish and other species that can have the ability to survive in Arctic climates because they have the capability to suppress their freezing points. And so take this beetle, I'm not going to try to pronounce the name, but it contains glycol proteins, and it's believed to be able to, again, survive in Arctic climates just because of that capability. And so perhaps this type of protein could be the inspiration behind smart passive anti-icing coatings. Lunar dust, another technical challenge that we will not be able to get around if we're going back to the moon. And so during the Apollo missions, the lunar dust not only posed a health hazard to the astronauts, but it also caused equipment and instrumentation damage, in addition to abrasive damage. And the dust mitigation strategy back then were brushes. But there are a lot of, a few different types of bio-inspired approaches that could be used. I know many times when we talk about dust or self-cleaning surfaces, oftentimes the lotus leaf comes to mind. But usually we have to think about the way that the lotus leaf is able to remain cleaned is because of the presence of dew or rain attaching to the dirt and rolling off the surface. In a lunar climate, you can't rely on that. So what are other strategies that can help keep the surfaces of our equipment and our instrumentation and the astronaut protective gear clean? There could be a number of different approaches, both passive and active approaches, either self-actuating systems or electroactive or other stimuli-responsive polymers, and even gecko feet that have the little nanofibrils at the surface or at the foot pads. And speaking of functional surfaces from the nanofibrils from the gecko feet, surface functionality is prevalent in nature, and it's this function that gives many species the capability to display very unique characteristics. And so one application where this could be useful is microbial filing and contamination. This can lead to, microbial filing can lead to corrosion of parts, fuel blockage, fires and explosions, and other issues where it degrades our parts. But marine lives don't have these issues. And so it's believed to be able to be effective in this area is because of the presence of microtextured surfaces like you see on this shell. And so it's believed that those microtextured ridges can actually disrupt the biofilm formation, thereby halting the growth of these biofilms. So that can be another route. And then finally, talking about limitations in synthetic reinforcement. So I really appreciate the previous talk because I too, we're here, Lorenzo, on that. But so there are many issues or many great things related to synthetic fiber reinforcements, especially copper fiber. It has high strength to weight ratio. We've been able to benefit substantially from lightweighting these composite structures because it helps with efficiency. And depending on the application and your anticipation of the types of mechanical loads and stresses, you can design a part with the appropriate layup and fiber direction. But there are some limitations. Either it can relate to environmental challenges, like in the case of aramid polymers or fibers, but also it makes the high. There's often a stiffness to toughness trade-off that you have to make. And then the other challenge relates to the fact that if you need a part requiring a complex geometry, you are limited in that area just because of the fact that these fibers are very stiff. But one model could be the conch shell. And so the conch has been found to possess both curved reinforcement and a plywood architecture. And so basically there were some researchers, Lee and Lee, who dissected various parts of this conch shell, and they performed fracture toughness, and they noticed that the areas of the conch that contained the curved reinforcement demonstrated a 30% improvement in fracture toughness compared to the parts that had the straight reinforcement. So perhaps this is another area where we could really benefit from nature in terms of improving the mechanical toughness and the longevity of our parts. Processing will no doubt be a challenge that we will have to overcome. In order to benefit from the performance and the properties that we find in nature, we have to be able to develop these parts and produce these parts at scale and at even the precision that nature often has. And we know that those two are cost prohibitive. Some polymer processing solutions that could be ideal or best mimic nature's bottom-up processing approach is self-assembly or layer-by-layer assembly, and also additive manufacturing. Nanolithography is also another technique that can be used to help form those nanoscale feature sizes on the surfaces. And we also know that natural systems form under benign conditions, and that is something that we can really learn from, because that is very attractive towards in-space manufacturing. And similar to that, along those lines, we currently have an effort that's funded through our Space Technology Research Institutes, where there's a team from UC Berkeley that is leading an effort related to biomanufacturing and biological engineering in space to help produce materials, energy storage solutions, energy storage devices, and also pharmaceuticals. That project was scheduled to end in 2022, but it's been continued for a few more years, and now will be ending in 2025. And so because our applications often require extreme environments, I often think about taxonomic bias, because I know that there's an issue with the over-reporting of some species due to their availability, but there's also a challenge related to the under-reporting of some species, because they live in extreme climates on Earth. Take, for example, Lake Natron in Arusha, Tanzania, in East Africa. It has one of the most toxic lakes in the continent, and the lake is red because of the cyanobacteria, but it's an extremely corrosive environment, and it has an extremely high salt content. Yet millions of lesser flamingos travel to Lake Natron every single year to breed, because it's a safe haven and they are protected from predators, because other species will just become calcified or their skin will burn off. So, so what is it about the flamingo that can give it the ability to thrive in this lake? The only thing that I hear is the tough feet, and that just doesn't sit well with me. But right, what is it about this particular species? And so, there's plenty of things that we could still learn. So there are plenty of opportunities to collaborate. I presented to you a few examples of where we could use more help in this area with other types of thinking than our own, others who have a knowledge of these biological systems, knowing how to stress them in ways that we can really, really see different parts about them, and understanding the mechanisms and how these species are able to do what they do. And to conclude, again, numerous opportunities available for which biomimicry can be used. And we do need advancements in materials and processing techniques. And we invite you to submit proposals in any of these areas. And I would like to acknowledge the aeronautics projects that we use to fund the self-healing insulation work, but also the sustainable manufacturing of aircraft project. And that concludes my talk.